Good day. Today we start a statistical inference, and the first technique that we are going to look at is point and interval estimation in chapter 9. These techniques are mostly used for marketing purposes and quality control in industry. So let's say that you buy a packet of chips or a box of cereal or a tub of yogurt, and it says 250 grams on the packet or the tub. Have you ever weighed it to make sure that it is actually 250 grams? Well, a manufacturer can't weigh the whole population of products to test it due to a lack of resources like time and money, but we can make use of statistical inference where we draw a sample of the products, test them, and then draw conclusions or inferences about the sample and generalize that to the whole population. So we work with two kinds of estimators in this chapter. Point estimators, where the parameter is estimated by a single value. For example, if I ask you, what is the average time that you drive to university? Or a parameter can be estimated by an interval estimation, like a confidence interval, where the parameter lies between two values, and you can say I drive between, let's say, 10 and 15 minutes to university. If you look at the outcomes in the study guide, you should first of all, for the theory part, understand the difference between point estimators and interval estimators, and then also name and discuss three characteristics of estimators. Then for the application part, you should be able to calculate these 3-point estimators, and then also calculate and interpret confidence intervals for population means, where we make use of large samples, and that means sample sizes greater than 30. Like I said, we are busy with statistical inference now. So statistical inference refers to methods used to make conclusions about the whole population from sample data. If we calculate a summarizing value from the entire population, we call that a parameter. And if we calculate that summarizing value for the sample only, we call that a statistic. But usually parameters are unknown, so they are estimated by statistics. So we can use the sample mean to estimate the population mean. We can use the sample variance to estimate the population variance, and we can use the sample proportion to estimate the population proportion. If the unknown population parameter is estimated by a single value calculated from sample data, then we call that point estimation. But if the unknown population parameter is estimated by an interval that is formed by two values calculated from the sample data at a specified degree of certainty, then we call that interval estimation, and then the interval is known as a confidence interval. Example 9.1 illustrates the difference between these two concepts. So let's say certain computer components are very sensitive to high temperatures, and the manufacturer of the computer components conducts experiments to determine the temperature at which the components will fail. Now, he wants to estimate the population mean, which is defined as the mean temperatures at which the components fail. Now, obviously, the computer manufacturer can't test all the components because he will risk damaging them all. So he can take a sample and then see when they will fail, and then he can calculate a point estimate or a confidence interval for the population mean. So if he calculates a single value like the sample mean and use that to estimate the population mean, that can be a single value, for example 50 degrees Celsius. But if he calculates, for instance, a confidence interval for the population mean at a confidence level of 90%, then there will be two values, a lower limit and an upper limit of that interval, and we can then say that we are 90% confident that the computer components will fail between 45.7 degrees Celsius and 55.2 degrees Celsius. Let's first look at the 3-point estimates. So if you have a random sample with n elements, then the sample mean calculated with this formula, where you add all the values of the different elements and you divide by the total number of elements, will be the point estimator for the population mean. Or the sample variance given by this formula can be used as a point estimator for the population variance. You are familiar with this formula from chapter 5. Your steps in calculations count marks, but you can use the shortcuts on your calculator to determine the sum of the square of the x values, for instance. Or the sample proportion, which is indicated by p hat, can be used as a point estimator for the population proportion, which is indicated by pi. Now we calculate the sample proportion by x divided by n. X is the number of elements in a sample that has some property, and n is the total elements in that sample. So for instance, if I want to investigate how many students in class have smartphones, then I would physically go and count, and that will be the count for the property that I'm investigating. So the count of students that have smartphones, and then I will divide by the total number of students in class. For example, they looked at the salt content of Frankfurter sausages. They sampled 10 sausages and they measured the percentage salt per unit mass, and these were the results for the 10 sausages. We want to calculate the point estimate for the population mean. We can calculate the sample mean. So you will add all the values for the 10 sausages and you divide by 10, and that will give us a sample mean of 1.957. If we want to determine a point estimate for the population variance, we first of all need to square all the values for x, and then we sum them, and then our n is 10 since there were a sample of 10 sausages, and the mean was calculated in the previous step, so you square that value. Please note that you only square the value of the mean and not of the product of n and the mean. And then we divide by n minus 1, and that will give us a sample variance of 0.159. Then they wanted to know what proportion of the Frankfurter sausages contains more than 2% salt per unit mass. So for x, you will physically go and count the number of values that were more than 2. So if you go and count them, it will be 6, and our sample size was 10. So our sample proportion will be 0.6. So we can say that the point estimate for our population proportion will be 60% of the Frankfurter sausages that contains more than 2% salt per unit mass. In example 9.4, they show you the values for 2-point estimators of the population mean. The sample median that had a value of 1.70 and the sample mean that had a value of 1.76. Okay, but how would we know which point estimator estimates the value of the population mean the best? Well, in order to decide, we must determine how the estimators behave in repeated sampling. So we look at the estimator sampling distribution. There are 3 criteria for a good estimator. First of all, the estimator must be unbiased. So for a fixed sample size n, the mean of the estimator sampling distribution must be equal to the true value of the parameter being estimated. So the unbiased estimator will be the most reliable estimator, and this will be the estimator that has the lowest variation or spread. For example, in figure 9.1a, they show you the sampling distributions for 3 different point estimators. They all have different spread or variation, but they are all concentrated around the population mean. So the point estimator with the least spread will be most reliable. So if you look at the sampling distribution in blue, it has a standard deviation of 1. The one in black has a standard deviation of 3, and the one in red has a standard deviation of 7. So the one in blue will be the most reliable estimator. 1.1b, they show you the comparison of a biased estimator that overestimate the population mean in this case, but it has small variation compared to an unbiased estimator, but it has larger variation. So we would prefer the biased estimator in this case, since there's a better chance that that estimator will have a closer value to the true value of the parameter being estimated. Secondly, we will choose the point estimate that is most efficient, and that will be the estimator that has the smallest standard error, and the standard error is simply the standard deviation of the point estimator. So under the central limit theorem, the standard error of our sample mean is given by the population standard deviation divided by the square root of your sample size. But if we do not have the values for the population, we can estimate the standard error by this. So the population mean will be estimated by the sample standard deviation. And then under the central limit theorem, the standard error of our sample proportion is given by the population proportion times 1 minus the population proportion divided by the sample size, and we take the square root of that. Or we can estimate the standard error by this. So the population proportion will be estimated by the sample proportion. Lastly, we will choose the point estimate that is consistent. So if our sample size increase, the sample represents the population more, so the values of the parameters and the point estimators will therefore be closer to each other as the difference becomes smaller. The next section looks at interval estimation, and a confidence interval is determined at a certain confidence level, or also known as the confidence coefficient, and it's denoted by 1 minus alpha. And this is simply the probability that the confidence interval contains the true parameter value. In this case, we are first of all looking at the population mean. And the confidence interval's lower limit is given by the sample mean minus the number of standard deviations from the mean times the standard error of the mean, and the upper limit is given by the sample mean plus the number of standard deviations from the mean times the standard error of the mean. Why do we determine the Z values at a half alpha? Well, if we have a 95% confidence interval, for instance, then the probability that the population mean will be included within the confidence interval will be this area under the curve, which is 95% or 0.95. So 5% of the time, the population mean will not be included in your confidence intervals. And because the normal distributions curve is symmetrical, it means that for 2.5% it will be below the lower limit, and 2.5% of the time it will be above the upper limit. But reading off your Z values from your Z table, as we saw last time, we look at the area to the left of a positive Z value. So that means it will include this whole area under the curve. So you won't look at a probability value of 0.95, but you will look at 0.95 plus 0.025. So that means we will look at the probability of 0.975. If we look for a probability of 0.975 in our z-table, that means that our alpha over 2 value will be 1.96 for a 95% confidence interval. You should be able to construct confidence intervals for a confidence level of 90%, 95%, or 99%. And if you look at the textbook on page 268, I've already looked up the Z alpha over 2 values for you, similar to the one I showed you for a 95% confidence interval, but just take note that there's a typo. For 90% confidence level, the Z alpha over 2 value will actually be 1.645 since it will lie between two values, so it's not 1.64 like they showed you in the textbook. Then just a note on the confidence level. If my confidence level increase, then my confidence interval will become wider since you are more confident that the population mean will be included in your confidence interval. So just to summarize, the confidence interval for population mean, if we have large samples, meaning a sample size greater than 30, is given by this formula. So the sample mean minus that product will give us the lower limit of our confidence interval, and our sample mean plus that product will give us the upper limit of our confidence interval. These are then the steps that we follow to calculate our confidence interval. So step 1, we specify the confidence coefficient or the confidence level. So that will be given to you in the question. Determine a 90%, 95% or a 99% confidence interval. Then in step 2, we determine our Z alpha over 2 values from our Z table, or if you know it off by heart, you can just plug it in. And then for step 3, we determine our sample mean and the standard error if it is not given. And then for step 4, you can calculate and interpret your confidence interval for the population mean. Let's look at an example. In example 9.5, they tell you a zoologist is interested in estimating the mean blood sugar levels in milligrams per 100 ml of a certain mammal after the animal has received a specific dose of adrenaline. The sample of 55 animals is chosen, so 55 will be our sample size, which is N. Then the sample mean is 126.9, that will be X bar, and the standard sample standard deviation is 10.5, so that will be S, and they ask you to construct a 95% confidence interval for the population mean and interpret it. So for step 1, our confidence level was 95%, so 1 minus alpha will be 0.95. For step 2, our Z alpha over 2 value will then be 1.96. Step 3, our sample mean was already given, so we just need to determine our standard error, which will be 10.5 divided by the square root of 55. And then we can plug in everything to determine our 95% confidence interval for our population mean. So our lower limit will be 124.125 and our upper limit will be 129.675. And then we just need to interpret it. So we will be 95% confident that the population mean blood sugar levels of all mammals of this type that has received a specific dose of adrenaline will be between that lower limit, and we go back to the units, it was milligrams per 100 mils, and that upper limit with the specified units. Then you always interpret it in the context of the problem, so just go back to the brief to see what we measured. Let's look at another example, exercise 1 at the end of chapter 9. They tell you in a sample of 100 people, so that will be N, it is found that the average amount of time it takes for them to drive to work is 35.8 minutes. So that will be our X bar with a standard deviation of 18.5 minutes. So that will be S. And they ask you to determine a 99% confidence interval for the population mean time it takes to drive to work and interpret it. So this will be our data. So for step 1, we know that our confidence level is 99%, so 1 minus alpha will be 0.99. That means that our Z alpha over 2 value will be 2.58, and our standard error will then be 18.5 divided by square root of 100. Then we have everything to determine a 99% confidence interval for our population mean. So we can plug in our values, and our lower limit will be 31.027, and our upper limit of our confidence interval will be 40.573. Then going back to the context of the problem, our interpretation, we are 99% confident that the population mean time it takes to drive to work will be between 31.027 minutes and 40.573 minutes. Your turn. You can try exercise 2, please.